Okay, so welcome everyone. Thanks for joining. Today we've got Wilma, who is a postdoc at MPA, to talk to us about Gaia and the fingerprints of the galactic bar. Wilma was a PhD student at MPIA, but I think she was also co-supervised by our very own Joe Bovey. And she's now a postdoc at MPA, and she's working on all sorts of fun stuff to do with the dynamics of the Milky Way and the imprints of non-axisymmetric structures on the kinematics and dynamics of the galaxy. So yeah, take it away, Wilma.
Thanks a lot, Ted, for the introduction, and I'm really happy that I can give this talk here today. Yeah, so the title of my talk is Gaia and the Fingerprints of the Galactic Bar, a Dynamical Milky Way Mystery. And I also want to mention the collaborators with whom the work presented in this talk has been worked on. Francesca Fragudi and Simon White here from Munich, then Jason Hunt and Ted McErath from across the pond, and then Joanna Coronado and Hans-Walter Rix from my PhD institute. So every good mystery story has a culprit. And in this...
I think your slides are not advancing.
No?
Sorry. Yeah, no, sorry. I thought we checked.
Sharing is paused.
So I think maybe the window has changed focus, so you just need to stop the presentation and then...
Classic. So
that's my fault for not...
No.
Do
you see now my second slide?
Yes, I think so. Yeah, that's it.
Yeah, okay, good. Good. So every good mystery story has a culprit. And in this case, it is the central bar of our Milky Way galaxy, which is this elongated, massive stellar structure in the galactic center, which is rotating with a pattern speed omega bar, which, even though people have been working on this like for 3 decades, this is still pretty much unknown. So the fingerprints are the suspicious motions that have been observed in the stars in the galactic disk, and where we don't know what has caused these motions. Our detective is Gaia, the astrometric satellite, and astrometry means very high precision measurements of positions of stars on the sky, and from this we can also derive Brabham motions and parallax distances. And Gaia also has a spectrometer on board, so it also provides the third velocity component, the light of sight velocity. The crime scene is the solar neighborhood, because most of the stars observed by Gaia are within a few kiloparsec around the sun, and especially there we have very high precision measurements. Of course, there's also other suspects that could cause these suspicious motions, like spiral arms or interactions with satellite galaxies. But in this work, I'm going to focus on the bar, because we know the bar is there and it should leave some fingerprints in the galactic disk. So my first chapter is called The Fingerprints Observed in the Velocity Space. I'm pretty sure that most of you might have seen this plot already. This was part of the second Gaia data release, and it shows the in-plane motions of stars within 200 parsec from the sun. We have on the x-axis the radial velocity of stars in the direction towards the galactic center, and on the y-axis the direction of tangential velocity in the direction of galactic rotation. And like in a perfectly smooth axisymmetric galaxy, this would look like a smooth, skewed, two-dimensional Gaussian, but you see it's pretty clumpy. And each of these clumps is a group of stars that moves with the same velocity vector in the galactic disk. But all these stars are spatially interspersed, and so there are some preferred directions of motions, and we don't really know why. So these famous moving groups, they have been really studied for quite a long time. So these two moving groups, they're called Pleiades and Hyades. They contain these. Do you see my cursor, by the way?
Yeah, we see it. Yeah.
Okay, awesome. Yeah, so here are these little overdensities that are the open clusters, Pleiades and Hyades. And so one of the first possible explanations was that these moving groups are evaporated open clusters that still move pretty similar to their original open cluster. This moving group is called the Sirius moving group because it's moving together with Sirius, the brightest star on the sky. And this very prominent feature is the Hercules stream. But since Gaia 2, we know that it's not just one stream, but it actually contains like 3 sub-arches. People have taken spectra of stars in these moving groups, and they found quite a large spread, both in their ages and in metallicity within one given moving group. And that means these stars couldn't have been born together because then they would have the same age and metallicity. So the moving groups seem to need to probably have a dynamic origin, so some gravitational perturbation that has induced these preferred motions. These 2 moving groups got more attention since Gaia 2. So we have here the head moving group, which is called like this because it's sitting on the velocity distribution like a head. And this is the horn because it protrudes from the velocity distribution like a horn, like a downward bending horn. Okay, now we come to chapter 2, which is called End Action. And here I'm gonna introduce the action coordinate system, which is really convenient to study the moving groups and also the effect of the bar. You know, our Milky Way is actually quite a complicated system. Like we have like the stellar disk and this dark matter halo. It's threaded by spiral arms, has the central bar, and then there's also the effect of interactions with dwarf galaxies. So one way to approach understanding this really complicated system would be to start with an axisymmetric Milky Way, like a gravitational potential that consists of a halo, a disk, and a spherical bulge. And throughout this work, I'm using as a background potential the Milky Way potential 2014 from Bowie. The nice thing about this kind of gravitational potential is that the disk orbits are pretty well behaved, so they have this nice rosette shape. And these rosette orbits can be considered as a superposition of 2 independent motions. We have, for one, the star moving on an epicycle around the guiding center with a radial frequency, and the guiding center is moving on a circular orbit around the galactic center with a tangential frequency. And now the actions, they're related to this in the following way. They tell us something about the sizes of these circles. So the size of the epicycle is related to the radial action JR. And the guiding center radius RG is related to the azimuthal action J phi, which is mathematically just the z component of the angular momentum. Now, these actions are in the axisymmetric system constant along the orbit, so-called integrals of motions, and can be used as labels for different kinds of orbits. And they therefore span the whole orbit space for regular orbits allowed in this gravitational potential. For those who like a little bit more of mathematics background, the actions are calculated assuming an axisymmetric gravitational potential model. And the general formula is the integral along the orbit over the velocity component in the corresponding coordinate plane for cylindrical coordinates for the galaxy. So for the azimuthal action, if we just insert the tangential velocity here, this is just r times the tangential velocity, which is the z component of the angular momentum. And that's related to the guiding center radius and the circular velocity curve of the potential. For the radial action, let's plot here the radial velocity versus the radius. And the star is moving between apocenter and pericenter around the guiding center. And from Stokes' theorem, by looking at this formula, it's the area that is related to the radial action, and so therefore it's clear that this formula is directly related to the size of the epicycle for the radial action. So throughout this talk, I'm going to show a lot of action plots. So I thought I'm trying to build a little bit intuition of what we see in this plane. So the radial action should be considered as a proxy for the amount of radial oscillation that the orbit experiences. And LZ should be considered as a proxy for the average radius where the star lives. And by definition, the sun, the circular orbit that goes through the sun sits at LZ equals 1, here on the circular orbit line. So any circular orbits inside of the sun would sit here on the left, any circular orbits outside then on the right. If we introduce now a little bit of radial motion, then we get orbits that oscillate around the circular orbit, but with higher radial action. This is with larger epicycles, and this with even larger epicycles. So I've integrated these orbits. I integrated these orbits only for a little bit, but if I integrate for a very long time, then each of them will fill a full annulus in the axisymmetric system, at least. So now one problem that we always have with any galactic survey is that only a certain part of the galactic disk is covered. And so as you can see, any of these yellow orbits would cross the survey volume, so can be observed. But from the orange and the green orbits, only those with really large epicycle and therefore large radial action can be observed. And this automatically leads to this outer parabolic envelope that any action distribution that I'm going to show for Gaia will have. Okay, so this is now the first action distribution that I'm going to show in this talk. But here, basically for the naive expectation of in an axisymmetric smooth galaxy simulation, radial action versus angular momentum for a survey volume of 3 kiloparsec. That's why we see here this outer envelope. And we also see these gradients, like one in the radial action, which means we have in this cold population mostly near circular orbits, and another one in LZ, which means in an exponential disk, we have less stars further out. So this was our naive expectation, and this is what Gaia DR2 has actually observed. So we get all these general trends, but the distribution is threaded by all these ridges. And I think I've counted like up to 3 ridges, and now Gaia EDR3 has found even more ridges further out here towards the anticenter. Yeah, and it's really the big mystery what this is. These ridges are related to the moving groups. And just to remind you, the moving groups have been originally defined for the little Hipparcos volume of 200 parsec around the sun. And this action plot is made for all Gaia stars within 3 kiloparsec. And if I locate stars from the different moving groups here in the action plane, they live here down at the near circular orbits, and the ridges basically come out extend from these moving groups. So the ridges extend the moving groups, or vice versa. The moving groups are basically just the local projection of this underlying orbit structure of the galactic disk that we see here in action space. So another property of these ridges that we see here is shown in this figure, where we color-coded each little bin according to the fraction of inward moving stars. So red means these features are mostly outward moving, and blue means stars are mostly inward moving. And as you can see, these ridges are really related to very strong preferred radial motion directions. Okay, now we come to chapter 3, bar resonances in action space. And let's see here what the bar is doing to an orbit. I'm going to explain this with an example orbit here in the axisymmetric disk, a nice reset orbit with tangential frequency and radial frequency. And because in the axisymmetric system, the actions are integrals of motion, this orbit corresponds to just one single point in action space. Now let's introduce a bar perturbation that's rotating with a pattern speed. And as you can see, with the same initial position of the star, the orbit looks now much different. So if I go back and forth, you see that basically the average circular radius in black moved a little bit outwards, and also there's more radial motion in general. And this is mirrored here in the motion in the action plane. So I'm still calculating the actions based on the axisymmetric background potential, but this is now the wrong potential. So these actions, they're not conserved anymore in this in the overall system, and that's why the star starts moving here in the action plane. And you see it moves towards larger LZ, to larger radii, and also towards higher JR, which means more radial motions. Now, this is a very special orbit that I picked here, and this becomes obvious when we switch into a coordinate frame where we are sitting on top of the bar and move and rotate together with the bar. And in this relative frame, in this co-rotating frame, you see that while the star is going once around the bar with this relative tangential frequency between the bar and the star's tangential frequency, it's going twice inward and outward. And we can express this relation in terms of the frequency, like here, this 1-to-2 symmetry. And this is actually a resonant orbit at the 1-to-2 bar resonance. And this special resonance is called the outer Lindblad resonance, or the OLR. If we now look at the way how the actions changed, and we see that they are also coupled by a factor of 1/2, just as the frequencies. And this is a very nice and simple result. It's already quite old, and this is a direct result of the conservation of the Jacobi energy. And this is also general. So this is for any L to M bar resonance. And in this system, the energy and the actions are not conserved anymore, but the Jacobi energy, which is the energy minus pattern speed times angular momentum, is constant. And if we combine this with the resonance condition and that the energy stored in the motion of the ith coordinate direction is frequency times action, we directly result in this simple relation, which is really good because it tells us that the behavior in this wrong action frame, the axisymmetric action frame, is still quite well behaved. Now the problem is that we don't know the real bar, so we can't really integrate just in the known bar potential with the orbits and check their frequencies. But what we can do is that we use the axisymmetric background potential and just do an instantaneous estimation of the orbital frequencies of the star if they moved in an axisymmetric potential. And if we locate any stars that satisfy this condition in action space, they would lie along this negatively sloped line, the axisymmetric resonance line. And as you can see, our example orbit is definitely related to this resonance line. So first of all, we get some scattering basically of the average, time average action of the orbit upwards towards the resonance line, and then some subsequent libration or oscillation of the star around the resonance line. So this was the behavior of just an individual star particle. So let's see what the bar would do to a whole stellar disk. For this, I set up a very simple test particle simulation, initially axisymmetric. Here you see the action space at the beginning very nicely and smooth. Then we introduce a quadrupole bar that rotates with a certain pattern speed. And after orbit integration of 25 bar periods, that's roughly 4 gigayears, you see that like these ridges have developed in the distribution. So luckily in my test particle simulation, I do know the pattern speed. So what I can do is that I overplot the resonance lines for different L's and M's, so for different kinds of resonances. And you can see that like the most prominent ridge that has developed right next to the OLR resonance line. And based on what we learned earlier, because many stars actually get scattered from the lower left to the upper right, we get this scattering ridge to the right. So this is one of the bar fingerprints that we expect a scattering ridge to right next to the OLR resonance line. And the same is also happening at this higher resonance, the 1-to-1 resonance. Here I'm showing the oscillation midpoints where I'm just taking the time average action along each orbit. And yeah, and you can see basically that around the resonances does really pile up along the resonance line, and then they will oscillate around the resonance line. And this is also a way to basically locate parent orbits in action space. So what is a parent orbit? Here back to our example orbit, I'm overplotting its parent orbit in black, and you can see that it also has the symmetry of 1 to 2, but it's closed. So after one go around the bar, it's closed. And these two orbits, they both belong to the X11 orbit family, which are orbits aligned with the bar. And here in action space, I'm overplotting as this little black dot the action of the parent orbit. And you can really see that the parent orbit would be close to the resonance line, and let's say the librating child orbit is oscillating around the parent orbit. Here I'm color coding the parent orbit according to if the star would be inward or outward moving along the orbit. And as we know, the sun is like 25 degrees to 30 degrees behind the bar. So we would expect that X11 orbits, as seen in the solar vicinity, should be inward moving. Here I'm again color coding the oscillation midplane, action plane, according to the orbit orientation that I just calculate according to the extent in co-rotating X and co-rotating Y. Red means the stars are anti-aligned with the bar, and blue means stars are aligned with the bar. And this very nicely illustrates this quite well-known and old result that at the main resonances co-rotation and OLR, the orbit orientation flips from aligned to anti-aligned. And at the sun, we expect that like the anti-aligned X12 orbit should be outward moving, while the aligned X11 orbit should be inward moving. And indeed, if we just take like a little circle, a little cylinder around the sun and plot it according to the radial velocity asymmetry, similar to what I showed earlier for the Gaia data, then we see that around the OLR, there should be a flip from red outward moving to blue inward moving. So this is another of the bar's fingerprints that we expect an outward inward motion flip due to the orbit orientation flip at this resonance. So the idea is now that we take the Gaia data and which is full of these red and blue stripes, and then move the axisymmetric resonance line across this plane by varying the pattern speed, and just position by hand the line between a red and a blue feature. And then we read off the bar pattern speed and therefore get some candidates for the OLR and the pattern speed of the bar. So the most prominent red-blue feature is this one between the Hercules stream and the head moving group. And the value that I measured from this 51 kilometers per second per kiloparsec is spot on the pattern speed of the classical fast bar pattern speed that has been around for over 20 years from modeling the Hercules and Horn with the OLR. The second prominent red-blue feature lives here within the Horn moving group. And this is a pattern speed of 33 kilometers per second per kiloparsec. And this recovers the slow bar pattern speed in the literature, which agrees with also some recent local modeling efforts, and also agrees with some older galactic center measurements about how the bar seems to rotate in the galactic center. So this is a slightly weaker candidate. Here, this is the Hyades moving group. Here's the Sirius moving group. The red-blue flip is down here and maybe also up here, red-blue. I don't know what this is doing in between. But if we just assume that this was the OLR, then we get a pattern speed of 45 kilometers per second per kiloparsec. This model was only proposed like 30 years ago by Carl Nice and hasn't gotten much attention since then. So I think this is a weaker candidate. What I really like about this plot is that it somehow just with one plot recovers a lot of the favorite models in the literature at the same time, except one, and that's the most recent measurement. So Jason Sanders and collaborators and Joe Bowlby and collaborators have, using the Tremaine-Weinberg method with measurements of the proper motions towards the galactic center, found a pattern speed for the bar, like the slow, slightly faster slow bar of 41 kilometers per second per kiloparsec. But if I overplot the location of this here in action space, it's just here on this blue stripe. So there's really no red-blue flip anywhere close, maybe here a blue-red flip, but that's the wrong way around. So this is a disagreement that is persisting, just that the local features don't agree with what we measure in the galactic center, and I haven't wrapped my head around what's actually happening here. Okay, let's come to the second part of this talk in chapter 4, which is called Looking from a Different Angle. So the actions J tell us which orbit the star is on. But the angles theta, they change with time, and they tell us where on its orbit the star currently is. They denote the orbital phase the star is in. So the azimuthal phase angle theta phi can be illustrated in the following. Here we have again a reset orbit in the galactic disk. Here's the galactic center, here's the sun, and here's the guiding center of the epicycle. And theta phi is just the azimuth between the sun and the guiding center. And this one increases linearly with time with the tangential or the phi frequency. So the radial phase angle theta r tells us where on the epicycle the star currently is. And we start at theta r equals 0 here at pericenter. Then theta r is increasing until it reaches apocenter at plus minus pi. And then it increases, but is negative until it reaches 0 at pericenter again. So here I have two example orbits. This is a non-resonant orbit, which is really just circulating around the bar like a reset. And this is our OLR example orbit from earlier. So imagine this is just a snapshot in time, this orbit, and this was populated with stars, and I calculated where would the stars lie in angle space. Then in case of the non-resonant orbit, the stars basically populate the whole 2 pi angle space. And these linear stripes, they come from the angles into increasing linear in time with the orbital frequencies. But this is not the case for this OLR orbit. So for the OLR orbit, we see that pericenters only occur next to the minor axis of the bar. And the azimuth of the minor axis is here, this dashed vertical line. And pericenter is here at 0. And you see that this orbit crosses pericenter and at the minor axis. So just from this intrinsic shape of the orbit and its 1-to-2 symmetry, we get that this orbit should lie around a slope of -2 in angle space. So one also says that the star is basically trapped to special regions in angle space or in here in azimuth. Yeah, so about resonant orbits, we also say they're trapped orbits. So this signature, this fingerprint of the resonant orbit can actually be generalized to all kinds of resonant orbits. Like here we have a 1-to-1 resonant orbit with just one pericenter, here one pericenter at the minor axis, on the 1-to-4 orbit, and a co-rotation orbit, which is just sitting on one side of the galactic bar. And it's always the slope of -m/L. And now the idea is, can we just plot Gaia stars and check if there's any slopes of -m/L in there, and then identify which resonance we're actually looking at? Okay, let's do this just for the OLR. For this, we first need to isolate some stars that belong potentially to the OLR. So I checked in the test particle simulation where most of the OLR stars lie. So this is color-coded, action space color-coded according to the fraction of resonant OLR stars. Here's the resonance line. And as you can see, most of these all our orbits live actually in this scattering ridge. So to test this with a test particle simulation, I take the whole disk. I get action space, I select stars in the OLR ridge, which I know. And indeed here in angle space, I get the slope of -2 in the OLR ridge, just due to this 1 to 2 orbit shape. And I could use this to identify the OLR. Okay, but there's some problems with the Gaia data, and that's that we don't have data for the whole disk. So again, we only have a certain region of the galactic disk, and this really strongly reduces the area in angle space that we can actually observe. So we're just seeing basically mostly stars between these two blue lines. So here the x-axis is much shorter. But at least there's still some potential overdensity of a slope -2. But it doesn't end there, because also the further out Gaia observes stars, the less stars can actually be observed. So there's a completeness decreasing with the distance from the sun. And if in my test particle simulation, I also apply like a very simplified completeness function, then all I see here is basically just this S shape, which it's a pure selection effect. So this gray line means that the azimuth is 0. So this is this line basically. Here's most of the stars. So when stars accumulate around this gray line means I'm mostly seeing selection effects. Now the question is, can I make the physical signature of the OLR visible again? And the idea that I had was making use of the symmetric shape here in angle space. So I'm taking here a bin which contains stars that are currently outward moving and have their guiding center in front of the sun. And if I mirror this by 0, 0, then I get here stars that are currently inward moving and have their guiding center behind the sun. And then if I calculate the relative number difference between mirrored bins, I basically take out the selection effect. And in this relative residuals, I get this red-green pattern, which is really nicely separated by a slope of -2, like the physical signature is made visible again. Okay, I have lost half of the information in angle space, but the signature is there again. Okay, now we come to chapter 5, searching for the bar's fingerprints in angle space. So let's actually look in the Gaia data for the OLR in angles. So step 1 would be, I take the Gaia action space. Here I'm marking with these lines with the black border. These are the different moving groups that we know. And then I'm just assuming some bar pattern speed and overplot where the resonance line for the OLR would be. And then I select stars just here to the right of the resonance line. And then I plot the angle space asymmetry pattern, which I will show on the next slide. And then compare it to the model prediction for the true OLR from the test particle simulation, where we should get a red stripe and a blue stripe separated by a line of slope -2. And then step 4 is just repeating all of this with a different bar pattern speed. And by doing this, we can basically scan across the whole action space and investigate the different sub-selections in angle space. And this is now how the Milky Way disk looks in angle space as seen by Gaia DR2. For different pattern speeds, I'm giving the bar pattern speed here in units of 27.5 kilometers per second per kiloparsec. Here's again the model prediction for the test particle simulation. And in principle, I could give you now some time to search if you think there might be a candidate for the OLR. But just to save some time, I think like the two best candidates might be here 1.2. Here's red and green, and potentially also 1.4, where here's red and green that might have here a slope of -2. There's a few more potential candidates, so just to give the overview, I'm showing here just the candidate angle planes. I'm also now plotting this gray line, which points out the azimuth of 0, so where the sun sits, because this could point towards potential selection effects. And while this plane has, interestingly, the same pattern speed as the head candidate from earlier, we don't cover much of angle space with the Gaia data, and also it could be that the selection effects have a similar slope than the OLR line. So I'm not 100% sure that what we see here is maybe not just a selection effect. The second candidate looks much better because here the selection effects are slightly different. And interestingly, this pattern speed of 39 kilometers per second per kiloparsec is pretty close to this pattern speed of 41 measured by Sanders and Bovey in the Galactic Center. This 44 kilometers per second per kiloparsec is would position the OLR next to Sirius, but I don't know, like it has this big green blob here, so I don't know if this little section is meaningful. And this 48 kilometers per second per kiloparsec, I don't know if it's really convincing, but friends of mine said they think there could be something, so I included it just for completeness. And not to be biased by the pattern speeds that I know are favorites in the literature. So let's compare this to the first method that I presented in this talk, where we looked at action space and checked for the red-blue flip. And yeah, here at the head, we had this very nice red-blue flip done for this pattern speed that also comes from the Galactic Center. As we see, there's no red-blue flip, but this blue-red flip. And therefore, I call this like the obscure or the obscured series pattern speed, because if this is actually the true OLR, something must happening that doesn't let us see this classic red-blue flip that we would expect. And for these weaker candidates, yeah, it's not really clear if there's a very convincing red-blue flip. Just for completeness, I'm also showing the classical fast bar for 51 kilometers per second per kiloparsec, where in action space, this is really the strongest red-blue flip. But in angle space, there's really no slope of -2. And also the selection effects look completely different. So we can't just say this is just selection effects. So I think that based on angle space, this classical fast bar should maybe not considered anymore. And then I want to finish up with a curious coincidence that I have observed in the data. I have no explanation for this, but I thought it was really interesting. And it was for this pattern speed of 38.5, like 39 kilometers per second per kiloparsec, the obscure Sirius pattern speed. And I can search as, so far I've showed you that I looked for slopes of -m/L for the OLR, which is -2. But I could also do the same spiel for higher order resonances, the 1 to 3 resonance, the 1 to 5 resonance, or the 1 to 4 resonance. And these resonance lines fall on in different regions on action space. And then select again stars to the right of this and compare this to this theoretical slope of -m/L. And it's not very strong, but here, okay, and here's again this weird green blob, but there might be a slope of -3 here. There might also be a slope of -4 here, even though this has to be taken with a grain of salt because of the selection effects. And also for the 1 to 5 resonance, we get here some slopes that could have the right direction. So this is really interesting, but the weird thing is that I couldn't make this visible in my simulation. So yeah, this is another open question that I think is fascinating, but I don't really know if this is just a really strong pointer towards this pattern speed being the right one, or if this is just a coincidence, I don't know. Okay, to finish up and the summary, let's play a round of clues. So this was basically mystery. So we had several suspects that could be several of these ridges that could be associated with the OLR. And we collected different clues about if this was a murder mystery, like was the suspect seen at the murder scene? Did they leave fingerprints on the weapon? Are there other clues? In our case, the suspects are the different ridges. If the Hercules is related to the bar OLR, this would correspond to a certain bar pattern speed of 51. If het is the bar OLR, this would correspond to a pattern speed of 33 kilometers per second per kiloparsec. The Sirius bar OLR, and then this obscured Sirius bar OLR. And the clues are, do we see this very classic flip from inward versus outward motion, which in action space? And then the second one, is there a slope of -2 in angle space? So if we test for the actual shape of the orbits, does it look like the OLR orbits? And then are there maybe other clues that point toward this being the true OLR? So the Hercules red-blue flip is very prominent, but it clearly doesn't have a slope of -2 in angle space. For the het pattern speed, we also do have an inward-outward flip. Because of some selection effects, it's a bit unclear if in angle space we see this physical signature of -2 or not. But there's also other indications that point to this being the true OLR. Like some papers say that for this pattern speed, the Hercules would be associated with the co-rotation resonance, and this could be consistent. And some recent papers also said that metallicities could also point, the metallicity distribution could also point to this being the right pattern speed. And then there's some older measurements from the Galactic Center that refer this very slow pattern speed. Here, the Sirius ridge being the bar OLR, it does have a inward-outward flip in action space, but other than that, there's not many things that point towards this being the correct candidate. And then this obscured Sirius bar pattern speed that very clearly doesn't have a red-blue flip in action space, but has a very nice -2 slope in angle space. And also it would agree with recent Galactic Center measurements. And there is this very suspicious angle signature at the higher resonances that also have the right slope. So how can we now decide between, is now the het the best OLR candidate, or is the obscured Sirius the best OLR candidate? And what I think what we need is, first of all, a little bit more data in the further out to just cover angle space a bit better with data to see if there's really this physical signature or if it's just selection effects, what we're seeing here. And then some other papers, they just claim that maybe spiral arms could maybe obscure part of this classic inward-outward signature. So we need some other models that don't just include a standard bar to explain maybe why here this red-blue flip is missing. And then last but not least, let's not forget that the galaxy very likely also has spiral arms, and how they will affect action and angle space is also still unknown. So this is, thanks a lot to listening to this galactic mystery story for which I still don't have as many answers as I would like to. But yeah, that's it. And thanks a lot for your attention. And yeah, I'm happy to answer any questions that you have.
Thank you, Wilma. That was great. We'll give you all a virtual clap. Great. Okay, so we already have one question in the chat from Julio, who asked, why couldn't there be more than one OLR? So shouldn't any m=2 perturbation induce one? Are there several candidates perhaps pointing to the presence of more than one m=2 perturbation in the disk, e.g. a two-armed spiral?
Oha, okay. The problem is that I couldn't test this in models because I just don't know which kind of spiral arm to put in there. So I have been co-author on a paper by Jerry Selwood, where he actually used different kinds of spiral arms models and just checked what kind of ridges they would cause at their resonances. And in case there was, like, we had a very nice spiral wave perturbation with a constant pattern speed for the spiral arm. And this creates very similar ridges, actually very thin ridges also at the resonances. So I think it could definitely be that just one of them is the true bar OLR and the other one is a spiral arm that just pretends it was an OLR. But usually, like for spiral arms, they have much slower pattern speed, so the OLR would be much more out, further out. So, yeah.
And does that, I guess not really line up very, there's lots of recent stuff showing that like the spiral arms maybe are like transient spirals rather than these like kind of long lasting.
Right. There, for transient spirals, Jerry also had a plot in his paper, which I try not to think about too much because when it's transient, then you basically the spiral arm basically sweeps through the disk with different pattern speeds if you consider in that plane, and that can really mess up a lot. And I think like there's this one. I remember that Jason Hunt pointed me to a paper from someone called Fuji or something, who ran simulations, and they also looked at this classic inward-outward flip, and they said that sometimes if the spiral arms are really strong, they can mess up, or they can mess with the signature that we're seeing from the bar. So disentangling this is quite a challenge that our community faces right now.
We have a hand up from Scott, so take it away, Scott.
Well, I'm not sure if this is a question or a comment, but I guess what struck me most about your talk is how hard this is turning out to be. I guess I would have thought that with the spectacular Gaia data and the fact that the bar is such a prominent feature in the center of the galaxy, that it should have been really easy to figure out exactly what the pattern speed was. So I guess I have two questions maybe. The first is, do you understand why it's so hard? And I got the second question is it clear that the bar has to have a constant pattern speed?
So I think the second one is slightly easier to answer. So there is this PhD student from Ralf Schönrich. His last name is Chiba, who wrote like two beautiful papers about the decelerating bar and its effect on the action distribution, and also on this red-blue feature. And it can shift, like a decelerating bar can shift the location of the red-blue flip with respect to the actual ridge, and it can also make the ridge like slightly wider. But at least the general trend was, when I just looked at their plots, was just very similar, and that's a ridge, like the OLR should cause a ridge, and that still stands even if a decelerating bar model is used and not a constant bar model. And then the other question, why is it so hard? Like, I think the problem is that there's many mechanisms that could cause just in general these ridges, and because this is where we have a certain relation between the frequencies, there can be some excitation of more eccentric orbits, and this can be caused by the bar, by higher order resonances of the bar, by spiral arms. But also, I think there was one study by Khanna in Australia who showed that also satellite interactions can cause even ridges and subfeatures. So I thought that was actually why I was looking into this angle stuff, because when so many mechanisms can cause the ridges, then maybe I should look at the specific orbit shapes, because the orbit shapes should contain more information about the kind of resonance that we're looking at. But angle space is super susceptible to selection effects, much more than action space, in fact. And properly disentangling selection effects and the physical signature. I mean, I tried it, but I don't know if I didn't use a function for the like sophisticated selection function to correct for this. So yeah, so I think that just calls for that we really need a super detailed selection function to correct for.
Okay, so another question from Yan Qing.
Okay, this is a question because I'm pretty ignorant. How if suppose the bar sort of started from 5 billion years ago, so it's not permanent, it's not constantly acting. What fraction of the star could actually feel this OLR, in the sense that if you're looking at your two different ridges, two different colors, what fraction of the star will be? How does that relate to the sort of intensity of those colors? Would that tell you the information?
Sorry, so if we go back to action space.
Yeah, this kind of plots.
Right. Yeah. So the stronger the bar is, the stronger this ridge. Because the region that is influenced by the specific resonance grows with the strength of the bar. But then also like what can be seen here, where I basically took the oscillation midpoints, the distribution of oscillation midpoints, that there's a lot of higher order resonances that also shows up here, right? I mean, I see stripes here. I mean, they don't, in the overall distribution, they don't, because of this libration around the resonance lines, we don't see anything here for the normal action space. But for the oscillation midpoint, it's clear that basically any region in the disk contains some resonances, and it really depends on the shape of the bar. So to first order, the bar is an m=2 Fourier component, but if it had more substructure, and there's one really nice paper by Giacomo Monari, where he showed that if he had a more complicated bar model with higher order bars, higher order Fourier modes, then these higher order resonances could be excited and also create these kind of scattering ridges.
Okay, so the higher order, right? Okay, so the higher order resonances could come in, but I guess I'm also sort of not sure that if the star was born a long time ago and then has been heated up, getting all kinds of radio and vertical actions and so on, and then you turn on the bar, would that change the picture dramatically? Is this all started from circular orbits?
No, this starts from this distribution. So I have eccentric orbits. I just have more circular orbits, and they also have different vertical actions. And in fact, it doesn't matter what your vertical action is. That means how vertically hot you are. If the orbit has the right in-plane frequency relation, it can experience strong changes induced by the bar. So it's not that it's just in the near circular and in-plane orbits, but any orbits can be affected by the bar.
Okay, thanks.
Cool. There's another question in the chat from Julio who says, I think this is kind of related to what you just said as well. Is it clear that the bar is a monolithic structure? Many spirals show complex bar systems with nested patterns with presumably very different pattern speeds. I was going to ask the question is that, like, when you look at face-on galaxy images, the bar regions are full of extra mass that is probably not just rotating and doing what we expect it to do in these simpler models. So can you comment on that?
So I have recently looked, like this is very preliminary work, and so some of my collaborators here at MPA from the Auriga suite, they're currently rerunning some of the Auriga simulations with a high, much stronger stellar resolution. So it's really like, it's called the Superstars suite. I don't know if it's already, if they already published any papers about this, but I was just interested because there was one of these simulations that has a really nice bar, and I just wanted to check in a cosmological context and with spiral arms if my methods to an angle space would actually work. And the really cool and really nice thing was that these angle slopes, that they should be actually there. Like in the simulation, they're very clear. So sorry, what was the question again? I don't know if I now answered it or if I
think so. So the question was, is it clear that the bar of the Milky Way is like a monolithic structure, or does it have maybe more complex mass distribution than?
I think it very likely will have, I guess, because it's never that easy. But the m equals 2 component, this one should be strong because then it wouldn't be a bar.
Right.
And so yeah. I think the OLR, because the OLR is the 1 to 2 resonance, should be strong.
Hopefully. Okay. We have a hand from Peter as well. But we are hitting the hour now, so we do need to leave. We'll continue the discussion a bit here, but otherwise, yeah. Peter, did you want to ask your question before we sign off?
Yes, yeah, thank you for your talk. Maybe further to Scott's question about why is it so hard, are there some diffusive mechanisms that mess up these resonances? Like I remember from the old days, there was scattering off molecular clouds and things like that, which would not be in your model, but would mess up your orbits somehow in a diffusive fashion, and maybe push them out of resonance or something like that.
I presume yes, because like doing what like searching for resonances, this has basically 2 parts. One is what orbits does the bar actually allow? Like for example, the OLR orbits, can we search for them? But then the other question is, how do we get stars on these orbits? Like, or the population history of the resonances, basically. And I presume that if there were some, I think this plays a role, but I just have no feeling how strong. I can just say that from this superstar simulation, the last plot that I made, like just a few days back, was that I color-coded basically angle space according to the age of the stellar particles. And I thought it was really interesting that the youngest stars followed very nicely these stripes, but in between these stripes were the more older stars. So I haven't understood yet what's happening there, but right now, at least in this simulation, it looks like that the features are most strongest in the young stars for whatever reason.
Mm-hmm. Yeah, I guess, I mean, like, presumably the GMCs will just, like, if you have a bunch of stars in the region of the galaxy that are on the same or a similar sort of orbits, right, it will just kind of diffuse more a bit, right? So presumably that's why the Gaia, like, plane looks all blurry, right? But anyway, we should thank Wilma again before people start leaving. So we'll all give you another round of applause. That was really fantastic.
Thanks a lot for having me here.
Oh no, it's been great to have you. Okay, unless there are any more questions or discussion points, I guess we can let Wilma go back to being on vacation. I'm gonna stop this.